Hello and welcome to my presentation Art Meets Science. My name is Sabine Heinz. I work as an artist in Berlin, and for my work I use different techniques such as oil or acrylic painting, collage technique and mixed media. What does art have to do with science? Consider that even as simple a task as sticking my brush into paint is an encounter with science, because the production of paint involves chemistry. But of course, it is only a superficial connection. In my pictures, I try to combine scientific content with artistry, but also to use scientific processes in an artistically effective manner. The starting point for one of my series was a lithograph that I manipulated in various ways by painting over it. Lithography, from the Greek lithos, stone, and graphene writing, is the oldest flat printing process. Alois Senefelder was the inventor of lithography, which he developed between 1796 and 1798. After much experimenting, he became familiar with the interaction of fat and water and developed planographic printing from this phenomenon. Lithographs are etched in stone slabs, which brings us back to chemistry. Here on this picture, you also can see a litho stone on the left-hand side, and on the right-hand side, you see the print made out of this. In the 19th century, lithography was the only printing process that allowed a bigger amount of color prints. Lately, I've been focused more and more on the inclusion of fluorescent and phosphorescent colors. This gives me the opportunity to hide things in pictures that only became visible when the pictures are stimulated with UV light. There are two pictures in one, so to speak. Here on the left-hand side, you can see one of the or in both pictures from this painted over lithographs. You see in the background the lithograph and what I paint over the lithograph. In the case of fluorescence, the light hitting the work is re-emitted at longer wavelengths. The science here is that the molecule in the paint or other medium has rigid bonds that cannot easily deform to absorb the incoming light energy and thus radiates again. Excitation and emission are associated with a loss of energy. Hence, the re-emitted light is at longer wavelengths. The fluorescence occurs immediately. Phosphorescence is slightly different. In the past, the dials of clocks were marked with phosphorescent paints so that they could be read at night. Phosphorescence is delayed fluorescence, which means that UV, ultraviolet light from the sun or from the UV lamp, is absorbed during the day and then re-emitted again for hours. Scientists have studied and described all these processes. In these pictures, you have a nice example between the fluorescence and phosphorescence. On the left-hand side, you see the picture during daylight. In the middle, you see the picture stimulated by UV light. And you see in the frame and in one of the trees that the fluorescence occurs immediately. But on the right-hand side, you can see I switched off the UV light, and the moon glow in the dark because he is painted with phosphorescent color. Here you have another example for the same process. I would also like to mention chemiluminescence, in which the substance luminol is oxidized with hydrogen peroxide. The process is catalyzed with a drop of blood or hemin. The oxidation creates energy that is dissipated as a bluish light. This process is a mechanism behind the so-called glow sticks. In a tube containing two chambers, there is hydrogen peroxide in one and luminol or an equivalent in an alkaline solution in the other. If you break the tube by bending it, the contents of both chambers will mingle and the glow will begin. Usually, there are also dyes added that will fluoresce or phosphoresce in different colors. Then there is bioluminescence. When I was in South Africa a few years ago, we would occasionally see thousands of glowing insects in the evening, known as fireflies. These beetles have a ventricular vessel in them similar to the glow sticks. The liquids are isolated from each other by a partition. In the event of excitement, fright, fear, warning, or the search of mates, this partition bursts and the glowing process begins. Since this is a biological process, it is called bioluminescence. The luminescent substance is luciferin. When living beings generate visible light through chemical reactions, this always involves the same principle. A fluorescent substance, luciferin, is oxidized with the help of an enzyme, luciferase, whereby energy is generated in the form of light. However, every organism has developed its own variant of bioluminescence. Different types of luciferins and numerous variants of luciferase produce light in all colors. In contrast to the yellow shine of glowworms, the fireflies, jellyfish and most other creatures of the deep produce blue or blue-green light. Here you have another example. Radiation at these wavelengths is highly adaptive as it penetrates water particularly well. If some organisms emit fluorescence light, this is due to an additional protein that fluoresces when excited by the bioluminescence reaction. One example of this is the so-called green fluorescent protein, GFP, from the Acorea jellyfish, which is now playing an important role in biomedical research for marking cells. The result will look something like what you see in these pictures. When the works are excited with UV light, they glow in the dark. You can see other bacteria I painted in an exaggerated form. And when you stimulate it with UV light, it glows in the dark. You have the coronavirus. And here's another example for coronavirus. So nice can be coronavirus if it is on a picture. GFP is a protein molecule and is built like a barrel with a dye molecule enclosed within. It is in a cage and therefore cannot move. Irradiated light is re-emitted as fluorescence. Hydrogen peroxide is a blue pale, also colorless and diluted form, largely stable liquid compound made of hydrogen and oxygen. It is a very strong oxidizing agent and as such reacts violently with substances such as copper, brass, and potassium iodide. In a highly concentrated form, it can be used as rocket propellant, either alone or as one of several compounds, but I didn't want to build rockets. I have made use of the oxidation process in my work with iron and copper primer. And I painted different portraits and then subjected them to the oxidation process by painting over them with various catalysts. The idea behind this was that just as with the aging process in humans, you don't know exactly what the result will be. You can exert only limited influence on this process. For these pictures, I worked together with a solar company, which is using algae to improve air quality. We combined parts of their algae carpets with my oxidation technique and tried to find out to what extent the oxygen produced by the algae acts as a catalyst for the various primers. Unfortunately, the results were not satisfactory in that we couldn't determine any significant influence on the oxidation process. Furthermore, we had to interrupt this work because of the coronavirus pandemic. However, further experiments are planned under laboratory conditions where, among other things, the oxygen content can be measured and we have tight containers. The problem is that if you have the pictures framed, air can enter and it's not really tight. And the algae carpet has to kept in a under wet conditions. So we are naturally curious to see where this effort will take us. Science and art are two different ways of approaching reality. Sometimes work of art say more about reality than science can because aesthetics and emotions plays a major role. As an artist, I can depict things differently and make them visible. As an artist, I'm not bound by the exactness of science. I can exaggerate things and therefore make them easier to understand. As for example, in this picture showing the surface on the moon, of the moon. But if I stimulate the picture with UV light in the dark, these tardigrades appear, which are extremophiles able to live in extremely harsh environments. In April 2019, the Israeli space probe Bereshit crashed on the lunar surface. This ill-fated probe had thousands of tardigrades, each less than a millimeter in size on board. And now Indian researchers found brown tardigrades, and by hitting them with really high doses of UV light, they turned blue or they started to glow blue in the dark. On this picture you can see a cosmonaut with the ISS over the Earth. And by stimulating with UV light, you can see the light pollution on Earth. Here you have the comparison of both pictures. And these pictures give an imaginative look at what it might look like beneath the icy skin of a watery moon. I think if there is life on such worlds, it exists in simpler form or in simple form. I have pictured here bacteria on the left-hand side, admittedly oversized again, but they would also have to be extremophiles who would need to endure a cold world that is perpetually dark. On the right-hand side, You can see two rivers who encounter, and maybe this also can happen under this ice surface on these moons. Let us now leave the scientific explanations aside and simply enjoy the pictures that were created in this way. And those try to build a bridge between art and science, not only thematically, but also in terms of color and technology and color experiments. And last but not least, I would like to show you some pictures from my digitally artwork. On the right-hand side, you see a new planet I invented. And on the next picture, you can see the Milky Way. And I have digitally animated, so you can see how it turns around. And this is more fantasy. It's called Starsea. And I make moving the stars into the sea. I thank you for your attention.